And what Cress is implying here is that the best way to reduce your cost per token is to actually move to the next generation Blackwell hardware. Hello, everyone. Today, we're going to unpack NVIDIA's fourth quarter 2025 earnings call. And specifically, we're going to dive into some insights that might not just pop off the page if you read the transcript or listen to the earnings call. So the first thing that caught my eye was when NVIDIA CFO Colette Kress was giving the opening prepared statements, and she read this quote: Blackwell supercharges reasoning AI models with up to 25x higher token throughput and 20x lower inference costs versus Hopper. So what stood out to me was the insight that what she's saying is that inference on previous generation GPUs is more expensive. So if you are a business who is doing inference at scale, the name of the game is reducing your cost per token, or cost per million tokens, really. You want to reduce how much it costs you per token, especially if you're selling an API. Obviously, if you're going to sell it for $1 per million tokens, you want it to not cost you 50 cents, but 40 cents or 30 cents or 20 cents, so you can make a higher margin, or so you can reduce your prices. And what Cress is implying here is that the best way to reduce your cost per token is to actually move to the next generation Blackwell hardware. Now, I think there's a lot to unpack, which we'll unpack another time, to ask why is the inference cost so much lower on Hopper? Is it because Blackwell has way more transistors per GPU, so there's more compute? Is it because of the FP4 support? And actually, NVIDIA's comparing apples to oranges here. They didn't say, right? So are they comparing FP8 throughput on Hopper versus FP4 throughput on Blackwell? We're not quite sure. They didn't tell us how they got this number. Surely it's a combination of all the things. Obviously, I think there's HBM3 on Hopper and HBM3E, which has a higher memory bandwidth on Blackwell. But if we take them at their word, then there are interesting implications of latest generation chips having lower inference cost than previous generation. Later, Colette also said, we've driven a 200x reduction in inference costs in just the last 2 years, which that is pretty crazy. So again, I'm emphasizing here that newer GPUs have a lower inference TCO than the N-1 generation. And so I kind of abstracted it here to say it's not just about Hopper versus Blackwell, it's about the latest generation versus the previous generation. And then of course I mentioned, well, okay, it depends on how you calculate it. If the prior generation is fully depreciated, then maybe actually the prior generation's costs are pretty good comparatively, even though you're getting less throughput. At that point, the hardware is free. But we haven't made a full depreciation cycle with Hopper. If people depreciate these investments over 4 or 5 years, it's only been 2 years. Okay, so why this is interesting is we are starting to get to a world where inference really matters and cost optimization, therefore, really matters to these businesses. So the first few years, totally all of the Hopper days really, were all just about a pre-training scaling. You had hyperscalers, infrastructure companies buying up all the NVIDIA GPUs they could, and they're turning around and then letting OpenAI, Anthropic, whoever use them, AI labs, use up all these huge clusters that were being built and all networked together to train the latest and greatest model. So the name of the game wasn't cost optimization. It was just throw money at scaling. Scale as fast as possible, build bigger clusters so that these AI labs could race to have the next greatest and best AI model. So, GPT-3, GPT 3.5, Claude, GPT-4. Now we're getting to the point, where there is actually a lot of inference happening. So ChatGPT, for example, 400 million weekly active users, and they're obviously not the only ones out there, but there is a significant amount of inference workloads happening to the point where surely it makes sense to try to cost optimize and say, how can we serve, especially with ChatGPT? I mean, they're charging $20 a month. A lot of those 400 million weekly active users probably don't even pay. And OpenAI hasn't introduced like a ad supported free business model yet. So, obviously I know they're making a decent amount of money. I can't remember the number off the top of my head. It was billions in revenue, but there's a lot more to be made. And so obviously they're clearly to the point where they have to say, how can we service all of this inference as cheaply as possible. And so the interesting thing that came out in this call is historically, we've all thought, oh, all these infrastructure companies, Microsoft, they're buying all these hoppers, they're using them for training. And then surely once Blackwell comes out, they will buy Blackwells and use all the Blackwells for training. So, latest and greatest, so you can train even faster instead of it taking, 4 weeks, maybe it takes 3 weeks. And you can just iterate faster and win that race. And then the question was, well, what will people do with their hoppers? And we all assumed that, well, then now they'll just serve their inference on the hoppers, because inference totally works fine on hoppers. You might get a higher throughput on Blackwell, but it'll be just fine. And so we all assumed that these big companies would use Blackwells for training and hoppers for inference. But what Colette said here on the call was that actually a lot of these Grace Blackwell deployments are earmarked for inference. So people are saying, well, of course we want Grace Blackwell for training, but we also want Grace Blackwell for inference. Why is that? It's because it's cheaper and they want to reduce their cost per token. At the same time, not only is there significant demand for inference broadly, but depends on how you define broadly. But regardless, there's also the amount of tokens being generated is increasing, not just from demand, but from reasoning models. On the order in the call, Colette pointed out on the order of 100x, right? So maybe if you asked ChatGPT a question and it answers in 300 tokens, maybe that same question or a different style of question, even a prompt to O3 reasoning model might take 30,000 tokens. And that sounds insane, but actually with all the internal reasoning that happens and then the response, 100 still feels like a lot, but I've definitely run distilled R1 from DeepSeek reasoning model locally so that I could look at all the tokens and count it. And we're definitely talking tens of thousands of tokens. So she's definitely not wrong. And so the point here is we are now in a world where there's a lot of inference happening and even more tokens being generated per request. And so clearly there's a great incentive to reduce token cost. So of course, now the question is, well, what about training? Are all these Grace Blackwell going to go to inference and are we going to slow down these huge Grace Blackwell training clusters? And the skeptic could say, well, Ilya says that pre-training scaling is dead because we've already consumed all the data on the internet. And so we need new sources of data. And of course, pre-training scaling, you have to scale data, compute, and model size together. So if you have more compute, but you don't have new data to learn from, who cares that you have more compute? Other skeptics will point to GPT 4.5, which was recently released, which used more compute, but isn't necessarily a new frontier model. It has a personality, maybe it has higher EQ, but it's not necessarily has advanced in its intellectual capabilities. And therefore, some skeptics would point to that and say, is pre-training scaling dead? Sure, it seems like it. On the other hand, you've got Grok, or I should say XAI with the Grok 3, Grok with a K here. And obviously, they showed that you can go from zero to having at least a currently frontier model just very quickly by buying 100,000 first and then doubling it to 200,000 hoppers. And you can see this tweet. They bought a ton of hoppers. They were able to quickly catch up to the frontier model. They're not even on Blackwells yet. There's still the data question, but their progress seems to hint that maybe pre-training scaling is working, or at least, and anyway, I guess my takeaway is there's enough uncertainty. It's not 100% clear that pre-training scaling is dead. And of course, there's still post-training RL that you can do and whatnot. So no one's going to stop buying GPUs yet. So they're still going to keep buying Grace Blackwells for training. But, and that's the interesting point that was made on the call, there's now incentive to take some of the Grace Blackwells and reserve those for inference. Okay, so, as we're talking about refresh cycles, and again, a natural question is, okay, fine. If Blackwell is more cost effective and Hopper's less cost effective, what happens to Hoppers? Obviously, today, we're sort of always sort of supply limited right now. And so if a company like Microsoft gets their hands on a ton of Blackwell, I'm sure they'll use a lot of it for training and they'll use some for inference. I don't think there's enough capacity for them to just say, I want to get as many Blackwells as I can, totally use all of those for inference, and we'll just get rid of the Hopper. But that's the question is, will Hopper be cannibalized by Blackwell? And Jensen sort of addressed that in the call. And how he addressed it was by demonstrating how useful GPUs are to generative AI R&D, research and development, even when they get to the point where they're not being used for production inference and production training. And so in this quote, you can see here, Jensen says, we're really good at end-to-end, we being NVIDIA GPUs, from data processing or curating the training data to the actual training, to reinforcement learning used during post-training, all the way to inference with test time scaling. So I bolded some of this parts here. Once you have data and you want to process it, GPUs can still come in super handy. So for example, let's say you are, and I'll give an example. Let's say you're Tesla and you're training maybe transformer-based vision models, and you want to look through all the data you've collected, real-world data, and look for a particular scenario. A great way to find a particular scenario. So for example, you might say like, I want someone who had to turn left at a green stoplight that's green, and they're turning left against oncoming traffic and it's snowing out. So it's slippery, right? So maybe they need to kind of slow down, and we want to see this scenario and train on this scenario and make sure that our self-driving Tesla knows what to do in this scenario. A great way to find that data, that kind of needle in a haystack of all the data that you have, which is all mostly probably sunny, is to use GPUs. And so now, do those have to be your absolute lowest TCO GPUs? No. Do they have to be your highest performant GPUs that would be perfect for training? No. You could totally use Hopper for this. The point here is that when Hopper sort of ages out of being the latest and greatest for training and inference, it doesn't mean that it's not useful anymore. It can totally be used for data processing. You can use it for reinforcement learning and post-training for fine-tuning. And by the way, you can continue to use Hopper for inference or for training. It's just going to be not as performant or not as cheap as Blackwell, but it obviously still works great. So test time scaling, you want to run reasoning models that think for a long time. Ideally, you'd run those on Blackwell, but during your peak demand hours during the day in the United States, for example, when everyone's awake, you might need to supplement your capacity with Hoppers. No problem. Nighttime, not as many people using it. Serve everything with Blackwell. And so Joe Flacco here as my analogy. So I like to think of my analogy for, a GPU that's now the N-1 or N-2 generation. It's sort of like Joe Flacco. He's 40 years old. He's still playing in the NFL. Look at all this, 2024 to present. Obviously, there was a time when he was the latest and greatest, and he was on the field, and he was the fastest, maybe not the cheapest, but definitely like the best player. But then eventually, as he gets older and not quite as fast, or maybe his arm isn't quite as strong, it doesn't mean obviously that he's not valuable. He makes a great backup. He's probably a great mentor to young players. It's just great to have on your team, probably an amazing scout quarterback. And of course, when you need him, if your first string goes down or something, he can come into the game and play. Might not have the absolute best outcome, but he can still get in there and the game can go on. And so that's my analogy for previous generation GPUs. Just think of Joe Flacco. Still very valuable. Okay, to continue to make the point, in the earnings call, Jensen went out of his way to mention that people are still using voltas, pascals, and amperes. So these are older generation NVIDIA GPUs. And I wrote here, note that these chips were launched many years ago, 2016, 2017, 2020. I think voltas and pascals are discontinued. I don't even think they still make them. Maybe they still make amperes, not 100% sure. But this just goes to emphasize how even if OpenAI, for example, isn't using A100s for inference, they can still find value out of them. And then Jensen pointed out that if the useful life is much longer, then the TCO is also lower. And so, total cost of ownership, obviously, if you have to throw something away after 2 years, or if you can use it for 8 years, the one that you can use for 8 years is sort of cheaper to use, whether you're depreciating it longer, kind of spreading out that life cycle longer, or it just gets depreciated quickly and then you're using it for free for all those future years. So he's clearly trying to make the case that our GPUs are super flexible. that makes them super valuable. They have a long life, so you can use them for a lot of things that benefit essentially from parallelism or accelerated computing, as he would say. And so the takeaway from the slide so far is that how you should think about this is NVIDIA making the argument with Blackwell that Blackwell's not only going to be preferred and in demand for training, but also for inference. So even if we were to hit a pre-training scaling hiccup and that slowed down, so long as we have demand for inference, especially if enterprises and apps start to find product market fit for Gen AI enabled features beyond just the blank text box in ChatGPT, which is still very valuable if you know how to use it. But imagine if it actually generative AI features start to get really built into your workflows. So long as there's demand for training and or inference, there'll be demand for Blackwell. And again, the demand for Blackwell is because for inference is because of that it's lower TCO, it's lower cost per token than Hopper. So point one, Blackwell is going to be in demand for both training and inference. Point two here is that Hopper's still useful, and it doesn't mean that that's going away. And point three, that the lifespan of GPUs are theoretically longer than you might think, given how flexible they are and how useful they are to various stages of the generative AI LLM workflow. And of course, they're GPUs, they're general purpose, they're useful for lots of other stuff beyond that too. So if you're a very large company, there's probably all sorts of corners of your organization that would benefit from using those GPUs, those previous generation GPUs. Now, one interesting counter argument that came to mind for me is like, okay, sure, they're useful so long as they don't fail. And the interesting thing about GPUs that are used for training, for example, is the high utilization. They're just used constantly, maybe for 4 weeks straight, 100%, like every minute they're just on in training and they're burning up, they're hot, right? You have thermal issues. They don't get a chance to breathe. It's not like they get hot and busy and then slow down. Maybe like maybe like a web server or something, like at least it probably gets to cool off at nighttime when everyone's asleep. Of course, unless the demand just gets shifted to other time zones. But regardless, like these GPUs for training just don't get a breather. And there's interesting, if you read the Llama 3 paper, how it was trained, they have this table here that shows all of the unplanned interruptions, and the majority of unplanned interruptions were just from GPU and their components failing. And a lot of that is, again, from stress and thermal events. So I'm sure we just don't know. I'm sure the life cycle of GPUs is long and they can be put to use for a long time, so long as they don't fail. There's a lot of evidence that there are issues in production training workloads, probably the same for heavily used during inference. What would be really cool is if some of these huge GPU infrastructure companies that buy a lot of these things, Microsoft, Meta, whoever, if they would share like a cohort analysis, like, hey, here's a bunch of GPUs that we bought 3 years ago, here's a bunch we bought 2 years ago, here's a bunch that we bought 1 year ago, and here's how many have failed. In the first 6 months, 10% fail, in the next 6 months, another 5% fail, and so on. And then, of course, if we could compare that over time, it'd be, as a cohort analysis, it'd be cool to see if that failure rate is going down or going up or whatnot. I mean, you can imagine with Blackwell, GB72, liquid cooled, 72 of them are all kind of scale up networked together. It would be interesting to compare that to, previous generations where it's only 8 of them connected together and maybe air cooled. Does liquid cooling help them to not fail as much? But there's 72 of them all hooked together, talking together during training, it would be fascinating and interesting to see, but we probably will never see that data. Okay. So that was like a big, interesting section of the NVIDIA earnings call. The next one is Jensen and Colette sort of spent quite a bit of time also positioning GPUs versus ASICs. Just given, again, back in December, Hock Tan made a comment about how they see like $60 to $90 billion of opportunity for XPUs from, I think, maybe 4 or 5 customers, and they talked about clusters of 1 million plus XPUs all on the same compute fabric. So think like Google TPUs. And I forgot about this earlier, but this could also be even like Chinese companies like ByteDance or Alibaba. Okay, so then a lot of people thought, ASICs must be the future, and that's going to negatively impact NVIDIA. Jensen spent a lot of time reminding people of the value of GPUs versus ASICs. And so first, this quote here, Jensen and Nvidia pointed out that we currently live in a world with 3 different scaling laws that we've seen for generative AI LLMs: pre-training, post-training, and inference time scaling or test time scaling. And the point they made is NVIDIA's GPUs can happily be used for any of that. You can happily serve them all. They're fungible, right? And so the quote from Jensen was, "We define Blackwell for this moment, a single platform that can easily transition from pre-training to post-training to test time scaling." And we've talked about this a lot before, that GPUs are general purpose and therefore fungible, interchangeable. The word fungible comes from when you're thinking about commodities. Like if I buy corn from this farmer or corn from that farmer, it's all just the same corn. It's fungible. Now, interestingly, that sort of implies that AI ASICs are not fungible, and that's not exactly true. Most AI ASICs are programmable and can be fungible. Not all of them. Some are much more fixed function. Also, obviously, like a Bitcoin mining ASIC is going to be very fixed function, very little programmability. But a lot of these AI ASICs, they are just systolic arrays or highly dense matrix math compute, max, multiply and accumulate units. And they're just laid out differently. They have sort of a different data flow, and they'll have like a different memory hierarchy than a GPU. So they'll still be very programmable. Google uses their TPUs for inference and training. I think Apple used Google's TPUs for training as well. But I wanted to make the point that Anthropic just had a discussion at AWS reInvent where they talked about how they're using Trainium, AWS's AI ASIC, for training and for inference. Well, actually, first of all, they're using it for Claude inference today, Trainium 2. And then there's this, which I think I have in my next slide. There's this quote where they said, "We're using Trainium 2 for fast, low latency Claude inference and working with AWS on a truly massive new Trainium 2 training cluster." And I think that cluster, it's has like going to have, I don't know, 300,000 ASICs. And so in this quote, they say, "We've learned a lot about the Trainium 2 chip architecture and really appreciate the flexibility and programmability of all the hardware engines. So you can use the Trainium 2 for training. You can also use it for inference." It's sort of funny that they named it Trainium 2, but you can use it for training and inference. Obviously, inference is just the forward pass through a neural network, and training is a forward pass, but also a backward pass, the back propagation for the training. And so, of course, you can use it for inference, but I don't know when they came up with the names, why they have a Trainium and an inferential chip when people are using Trainium for inference. Slightly confusing. But anyway, the point is that some AI ASICs are fungible. So I just want to point that out. But I also wanted to clarify that not all of them, not all AI ASICs were made to be great in a system for training, right? So whether that's they don't have the software support for all the communications primitives, or they don't have the networking in general. Some of them are just really focused on inference. And so not all AI ASICs are the same. I don't know if I have a slide for that. I can't remember, but I'll just make the point now. Not all AI ASICs are the same. And of course, the more sort of fixed function they are, generally like the higher performance you will have, relative performance or performance efficiency, because you don't have all that extra just bloat of being general purpose. So serving many different purposes. So all the extra circuitry you need to be general purpose. So like in the highest level sense, instead of having compute for FP16 and FP8 support, you could just support FP8 if you wanted and not have to have adders that can add FP16. Now, obviously, that's just an example, but the point is the more programmable it is, the less, totally fixed function, but also very fit to form it is. Like the lean, it doesn't have any bloat. If it's the trade-off is if it's still somewhat programmable, then it can still be faster than a GPU, but also be used for more than just transformer LLMs, for more than just inference. Okay. Now that also means, interestingly, the AI ASICs can be cheaper. You still might end up paying Broadcom or Marvell to help you, but you can have higher performance at a lower cost to build. And for certain workloads, ASICs can be more performant and cheaper, but there's definitely a switching cost. Anthropic is funded by AWS and therefore highly motivated to invest the effort and opportunity cost, something that we don't talk about but people sort of implicitly understand, which is, hey, wow, now I have to rewrite all my software to run on this AWS Trainium 2. Frankly, a lot of ASICs, AI ASICs, are used for first-party workloads by these companies, AWS, Google, and Meta with their Maya and Maya 2. They are incentivized to move their own workloads to this chip that was designed, for their workloads. Third-party developers, what's their motivation to move to Trainium 2 if they have to rewrite all their software? Interestingly, in that same AWS reInvent video, they made a subtle point, which is, well, don't we live in a world where you can just use AI to help you port that? So the argument is maybe the switching cost isn't as high as it used to be, and maybe it will continue, that barrier to switching will continue to get lower and lower. So they showed an example that you could use Claude to generate code to help you port more of Claude to run on Trainium. So the quote down here at the bottom, thanks, James. I just want to remind everyone that what we just saw was actually Trainium writing code to be used on Trainium. Super exciting stuff. The point is there's switching costs if you move to an AI ASIC, but maybe those won't be as painful in the future. Okay, so point that I made earlier, and I guess I did have a slide for it. Not all AI ASICs are the same. Some are less programmable. Some can't support training. Some don't have significant HBM capacity to run big models. But just a quick reminder that just because Anthropic can use Trainium for training and for inference for their particular workload doesn't necessarily mean that OpenAI is going to suddenly use Microsoft Maya or something else that they build for every single workload. GPUs are definitely the de facto until widely proven otherwise, because they're flexible and they work and everyone's using them. The installed base is there. There's no switching costs if you move from Hopper to Blackwell, maybe other than physical infrastructure switching costs like liquid cooling. Okay, so now that was a little bit of sort of a rebuttal to Jensen's fungibility, which of course GPUs are 100% fungible. Some AI ASICs are also fungible. And then I kind of went off on a rabbit trail there. But Jensen said, okay, also our system roadmap cadence is so incredibly fast, right? So they're bringing out new systems. So it'll be Blackwell and Blackwell Ultra and Rubin, and they're bringing out new CPUs. First it's Grace, and then it's Vera. They're bringing out new NVLink switches, NVLink 4, 5, 6, and then of course software innovations. And they're going from air-cooled to liquid-cooled data centers. And so just their cadence is so fast. Networking, memory, software, data center, they're just always improving. At a point in time for a particular workload, you might say, wow, an AI ASIC really pencils out. But the question is, can those roadmaps keep up? Is Trainium gonna continue to get better and better and better year after year? Because remember, every generation of Nvidia is bringing down your cost per token. Every single year, can Trainium reduce your cost per token? Maybe not. And of course, same with Google TPUs, same with startups. And then finally, Jensen reminded listeners that sure, on paper, we hear about lots of AI ASICs that are performant, and maybe they even get designed, and maybe they even get taped out, but do they get deployed? Oops, I didn't bring the right quote in. This is a copy paste error, but basically the quote was essentially like, sure, you can design these things, but they have to get deployed, and getting deployed is a business decision, right? You have to have business people who say, yes, we actually want to take up our limited data center space and use these AI ASICs, whether they're from a startup or internally built ones. And we think the dollars and cents make today, but we're also investing in a roadmap. We think the dollars and cents make sense tomorrow. He sort of said, cool, but I'm looking around and all I see is Nvidia. So where are the ASICs? And as a former product manager, I just want to say, if you build it, they won't always come. So this is Kevin Costner, Field of Dreams. Everyone here in Iowa is proud of this movie because it was filmed in Iowa. And in this part of the movie, he hears this, if you build it, they will come. Don't listen to that voice. If you build it, they won't necessarily come. Go talk to your customers and find out if they actually want it first, and if you're solving a problem that they actually have. So, and the same goes with, AI ASICs chips. Just because you build it doesn't mean it'll get deployed. All right. So lastly, what else was interesting from the earnings call that we'll talk about here is Nvidia talked a lot about Ethernet, which is really interesting because if you remember early on, everyone said, oh, the Nvidia moat, it's CUDA, it's InfiniBand. Now in the pre-scaling training race era, like that totally matters. And that was super important. Interestingly, when we get into an inference-heavy workload world, we're starting to hear lots of companies who say Ethernet is fine. Fast enough, we can overlap our communication and compute, so we can kind of maybe hide some of that latency. It's a lot cheaper than InfiniBand, and we're used to it. We have it in our data centers already. Everyone's familiar with it. Like, we're just used to it. And so turns out that a lot of customers were starting to say, we want Ethernet. And as I wrote here, rather than NVIDIA saying, oh, shoot, all those networking dollars are going to start shifting to someone else, maybe Broadcom, NVIDIA responded by creating their own Spectrum-X Ethernet, and it's optimized specifically for AI workloads. And so, of course, this fits NVIDIA's strategy really well, which is, hey, we're going to build these turnkey data centers, and we're going to optimize every piece of the system. We're going to optimize the CPU for AI workloads, obviously the GPUs. We're going to optimize the communication. If you want Ethernet, great, but it'll be optimized for these type of workloads. And so I thought it was a really good, it fits with their strategy, and it's a really good business move. And you can see that lots of customers want it. So, Colette called out that Spectrum-X enhances the Ethernet for AI computing and has been a huge success, and then calls out some customers, Azure, Oracle, CoreWeave, and then even the Stargate data centers. If they're built, they will use Spectrum-X. So I think this goes to show that customers are obviously thinking about cost optimization in general, even for training, because a lot of these clusters are training clusters. But I think inference especially will push for Ethernet. And then interesting, there's this little quote and where they said, they're talking about their networking business, and they say, we are transitioning from small NVLink 8 with InfiniBands, that would be Hopper, scaling out with InfiniBand, to large NVLink 72 with Spectrum-X. And they didn't really say that Spectrum-X is the default, but it kind of made it sound like when they sell NVLink 72, kind of by default, it's going to be Spectrum-X. I don't know if I interpreted that correctly, but I was sort of surprised that they're like shifting, saying, I don't know if that's just all the customers are asking for it. So it's like, okay, that's what you're getting. Or if I'm just misinterpreting this and you still can get InfiniBand with NVLink 72. I just thought it was an interesting quote and kind of a question mark for me. Okay, so one last thing. So it used to be, it was pre-training scaling, and InfiniBand was a differentiator. And then we're getting into sort of an inference world, and inference demand growing and the tokens growing. And also people are asking for Ethernet, sort of cost optimizing. Well, and so NVIDIA said, okay, we'll make Spectrum-X Ethernet. They also talked about Cisco and how Cisco is going to integrate NVIDIA's Spectrum-X into their networking portfolio. So I thought this was interesting. Partnering with Cisco gives NVIDIA a foot in the door with these enterprise data centers, with these on-premise solutions where people are already using Cisco. And as some of those customers say, hey, we want to start to stand up maybe Grace Blackwell or even Hopper, or maybe it'll be Rubin, and we want to put those on-premise, NVIDIA is saying, we're going to make it easy for you. You're probably already using Cisco. And so here you go, just buy this particular product from Cisco, which already has our Spectrum-X Ethernet built in. So I thought that was cool. I'm not sure the on-prem market is massive or will ever be massive, but it's still additive, and NVIDIA's going after it. I just thought this was a nice touch. Okay, we're still obviously very deep into this video. I actually cover a lot more interesting points behind the paywall. So if you go to chipstrat.com, you can read those. NVIDIA sort of used some language that made it feel like their revenue wasn't as concentrated as it always has been. I'm not sure that that's the case. I actually think it was just a choice of language, and that their revenue is still quite concentrated. So I talk about that. You can check it out. Jensen talks a lot on the call about sort of the future of AI as accelerated compute, and also we can see the future of software, and it's all going to be machine learning based. And I kind of go deep and ask the question, is that true? What about these use cases? And what is the impact if his vision is correct, but his timing is off? And then I talk a little bit about AMD. So NVIDIA is talking a lot about a particular value prop in this call that AMD has historically talked about. So are they sort of encroaching on AMD's territory? And then I address a question that people have had about, can AMD compete against previous generation GPUs? So the point has been made, well, AMD is not only competing against Blackwell, but don't forget Hopper's out there too. So if people are looking to cost optimize, might they just choose Hoppers which are $4 an hour, but maybe they'll go down to $2 an hour once Blackwell becomes very pervasive? Wouldn't they just choose Hoppers and not MI350 or MI400? And so I talk about that too. So if those are interesting to you, check it out, chipstrat.com. So with that, thank you for listening. This was a long one. I think a lot of people's reactions to the call was like, that was boring. They didn't announce anything and nothing interesting, just execution mode. But I really do think that as they sort of tip their hand to the shift from just scaling up training at all costs to companies now focused on inference workloads and cost optimizing, I think there's lots of interesting implications there. So I hope you enjoyed this talk, and feel free to leave comments on my YouTube. Feel free to shoot me an email and let me know what you thought. Talk to you later.